Hello, welcome to my channel Logically Literate. In this video series, I'm going to talk about how to communicate between a Raspberry Pi and an Arduino over a network. The basis of this tutorial will be using sockets and IP packets to communicate between a Raspberry Pi or any computer running a Python program and an Arduino running the C-like Arduino software. In this video we will talk about IP addresses and ports, transmission protocols over IP, byte packing and structures, byte order, and how to decide on your data structure. A couple of quick notes before we start. Most of this applies to the internet. There are some minor differences when you're talking internet versus local network, but for simplicity's sake we'll be talking about a local network. I may simplify some things, use some wrong terminology, but that's just because I'm explaining it how I understand it. If I make any mistakes, please let me know. Lastly, this is my favorite way to send data over a network because it's very easy to do using Python and can be pretty much done with any device that can connect to Wi-Fi or use an Ethernet port. You can use higher level, easier to use APIs such as HTTP over a network. But they do add more overhead, which can make data transfers take longer and things like that. So this is going to be very good for low latency, high speed data transfer. So to start off, let's talk about IP addresses and ports. The basis of network traffic rely on two basic numbers, your IP address and your port number. Think of IP addresses as the address to an apartment complex and the port number as the building or room number in that apartment complex. The IP address describes where in the world to find something, and the port number describes where on a device to send a specific message to. So when you create a program and you run it on a machine, you listen on a specific port such that when a request comes in for that port, it gets forwarded to the correct program running on that machine. You'll need both of these to target a specific process on a machine on an IP network. One other thing to think about is static versus dynamic IP addresses. Some networks, IP addresses are given out statically. Some are given out dynamically using DHCP. You'll want to know that before continuing in this process as to which one your network is. For most in-home networks, it'll be DHCP and it'll be dynamic. So you'll have to find a way to figure out what your IP address is before talking to your device from some other device. Now let's discuss transfer protocols, UDP versus TCP. UDP and TCP send the same type of packets back and forth, the IP packet as defined at the bottom of the screen. The main difference between UDP and TCP is connection-based, UDP is not connection-based. Because TCP is connection-based, there are acknowledgments of packets that get sent back after a packet is sent to the target device. For this reason, TCP can be slower. When TCP packets are sent over the network, they can be throttled and slowed down. However, UDP packets, when they get sent over the network and they're throttled, they are dropped. So you can't rely on UDP data transfer, but you can rely on TCP data transfer because TCP will retransmit the same packet if an ACK has not been received for that packet. UDP is good for fast data transmission that you do not necessarily need all of the data to be transmitted, so it's good for real-time data, whereas TCP is better for transmission of data where you need to make sure all of the data is transmitted from point A to point B. Next we'll talk about byte packing. In the previous section we showed a IP packet at the bottom, and the very last part of an IP packet is the data section. That is where the user can place their data structure to be decoded on the other end. You'll notice in this example here we have a struct of data that has two integers back to back. In a 64-bit system, integers are 4 bytes large, so this entire data packet would be 8 bytes. Now if we had different types of data storage containers within the structure, it could change the overall size based on its byte alignment, which we'll talk about next. So I won't get too in-depth about byte alignment, but I will say as much as you need to be aware that byte alignment is a thing, and that the length of a structure isn't always the size of each element summed together. You can check out that Wikipedia link there at the bottom. I'll also have it down in the description, but it gives you a good idea of how byte alignments happen on different types of systems. Basically what happens is you have padding bytes and you have certain byte sizes, and depending on the order of the bytes and the different sizes of that container, certain alignment is needed. So to retain that alignment, padding bytes will be stuffed into your structure depending on what order you put your data in. Knowing this, you can efficiently design your data structure such that your data containers or your byte containers are in such an order that you do not have padding or you have minimal padding in your data structure. Byte order is related to this. When packing bytes into a packet, you need to understand the byte order of your system. This is needed such that when you are decoding the bytes on the receiving side, you know which order to read the bytes, either from left to right or right to left, based on big endian versus little endian. There are two things to think about when deciding on a data structure. One, you need to think about your byte alignment. You need to make sure that the containers that you choose line up in the way that you expect them to line up, such that when you write your decoder, you're able to decode them properly and padding bytes don't mess up your program. Secondly, you need to realize the architectures you're using between the two devices that are communicating with each other. So on Windows, this data structure here would be 8 bytes because it's two integers back to back. An integer in Windows is 4 bytes. It's a 64-bit system in Windows, specifically, that we're talking about here. With an Arduino, it's a 16-bit system, so each integer is 2 bytes, meaning that this data structure will be 4 bytes. So if you're trying to send a data structure of integer to Windows from Arduino, and you use the word integer in Arduino's code, you're really saying a short in Windows. So when you go to decode it in your Python script, you need to use the decoding for short, not the decoding for integer, because in the Python program, short will be 2 bytes, but in the Arduino program, integer will be 2 bytes. Lastly, you need to think about your problem and what data you need to be sending back and forth. You may want to have multiple packets that you send to multiple ports because you want to send 2 different or multiple types of data. And so you'll want to think about how you can use the data on your receiving side and how you can correlate that data to be useful across possibly multiple receiving ports or even just multiple different packet types, and how you can correlate them together. So maybe you want to include a time of sample taking, or maybe you want to have some sort of ID number that goes along with each packet. In the next video, we'll be talking about how to actually write the software, and I'll give some examples of some Arduino code and some Python code. The Arduino code will be a little bit more in depth because it's using C-based language, and the Python code will be a little bit easier to consume. It'll only be a couple lines of code because we're using the struct library, which is very easy to understand. If you found this video helpful and informative, please like and subscribe, and I'll catch you in the next video.